Hello everyone, welcome to today's Wolfram live stream. Today we have Nathan Magari, and he'll be talking about gravitational waves in discrete spacetime.
Yeah, so thank you for having me. It's a pleasure to be here, and I'm excited to talk about my project. It was last summer, so I did have to refresh my memory a little bit. But I I do have a slide for introducing myself, so I'll start sharing my screen.
Go ahead.
So this is the presentation I put together. Like you said, my project was on gravitational radiation in discrete spacetimes. And a little bit about me first. I'm a UCLA alumnus. I studied applied mathematics and astrophysics, and I graduated last year. After graduating, I attended the Wolfram Summer School, and I worked on this project. And afterwards, I returned to Los Angeles, and I'm currently working at the infrared laboratory at UCLA. And right now, the project that I'm working on the most is the Liger spectrograph, which is an integral field spectrograph that we're working on for the Keck telescope to go with its new adaptive optics system. So I'm primarily interested in instrumental design, but I also have a strong interest in computational physics and astrophysics. So that's what drew me to this program last summer. And I really enjoyed my time there and met a lot of really great people. So a little bit of a background and outline of what I'm going to talk about. I'm going to go over kind of what I had to learn first before delving into this project, because I had only taken one undergraduate course on general relativity, and so I had to kind of teach myself a lot about gravitational waves and types of radiation before trying to create these models. So for the background, we're going to talk a lot about the continuum paradigm, types of radiation in the space-time continuum, and the motivation and challenges of going discrete. And then I'll talk about the models that I focused on within the Wolfram class of models, and finding specific rules to simulate gravitational waves. And then I'll go over the initial conditions and simulations that I ran. And then I'll do a brief conclusion. Okay, so for the background, we're going to start with talking about the continuum paradigm. So it should be pretty obvious that any physical theory needs to have a good description of space and time. And historically speaking, the notions of space and time, whether they're continuous or discrete, has been a philosophical argument for thousands of years. And these kind of debates and thought experiments about space and time have led to many of the pillars of mathematics, such as geometry and calculus. And ultimately, the importance of this is that space and time compose the arena in which all particles, objects, events, and people, the observers of those events, exist. And so their mathematical description is a prerequisite for any physical theory. And with Newtonian and classical mechanics, there was this absolute notion of space and time that any two observers can agree on um, on what time it is and how much time has elapsed between two events and what the distance is between two events. But it quickly became clear through experiments on the speed of light that that was not the case, because experiments trying to measure the speed of light in different reference frames resulted in one of the most important results in modern physics, which is that the speed of light is constant for any observer who measures it. And so Einstein's theory of general relativity describes a different kind of space-time continuum, but there's still a continuous space, meaning that between any two events, you can subdivide infinitely many times and find infinitely many events between any two. And so the structure of this space-time continuum is determined because this constancy of the speed of light is taken as an axiom. The structure of the space is determined by the possible paths of light through each event. So it's really the paths of light that determine how this space is connected. And this is a good illustration of what I mean by that. So in order for it to count as a space-time manifold, that means that locally any event has possible paths of light leading through it, which form this conical structure. And for flat space, which is devoid of any mass or energy, these are perfect cones where the circles just spread out at the speed of light. But overall, even though that's the local geometry, the global geometry can be curved. And so one particular example of that is if we have a black hole, these light cones are curved so that the future paths of light. And okay, one thing that I should probably specify here is that this is trying to depict a drawing of a three-dimensional object, but one of the dimensions, the vertical direction, has been replaced by time. So instead of considering the vertical direction as a spatial direction, we're picturing it as time. And so this orange cone represents the past light cone of this event E. And these are all the possible paths of light that could reach event E from the past. And the blue represents the future light cone. So an example of how this space could be curved is if you have a black hole, some compact object which is curving the space. At some point, if this event gets close enough to the black hole, the future light cone will be curved so far inward that it will never escape from the black hole. So that's why black holes have this surface called an event horizon. It's because they affect the curvature of these light cones.
So we're looking at the connectivity of space that's sort of determined by you go to a point You look at like where you can travel from that point to like neighboring points,
Exactly, yeah.
and and those so that we're using like a geodesic patch essentially, our space-time manifold, and we're using light rays as our geodesics.
Exactly, yeah. So the light rays form what are called null geodesics because um, using using the Minkowski metric, which we'll talk about a little bit later, um, the the metric is defined so that um, distances between any 2 points that could represent um, the path of light, those points have a distance of 0 between them. And anything within the cone has a positive um, notion of distance, and anything outside the cones has a negative notion of distance. So yeah, the
And that's measured in the Minkowski metric.
exactly, yeah. So it's not our normal um, kind of everyday notion of distance, but it's a function of both the amount of time elapsed in some coordinate system and the yeah, it depends on the exact coordinates that you use to define the space-time manifold. And we can see uh, these other paths represented by P1, P2, P3, P4. This is showing that any particle that passes through this event is constrained to be within the light cone, because any particle with mass, as one of the properties of this space, it cannot travel faster than the speed of light. And so it's constrained to stay within the future light cone. Okay, so yeah, I think we're ready to go on. So next I want to talk about types of radiation in the continuum, because we were talking a lot about light, and light is the most common form of radiation that we're familiar with. And in addition to being important to the formulation of general relativity, it's also important just in our everyday kind of observation of the world is primarily based on observations that we make in the form of light entering our eyes. So the term radiation in general just refers to energy which is emitted. It could be in the form of particles or waves, but it's energy that's released from a system and it's transmitted over long distances. So electromagnetic radiation was thought for a long time to be composed of waves in the electric and magnetic fields. And that's still a useful way of thinking about light. But we know now that a more complete description describes light as being composed of photons. And these photons can have different energy states. They can carry different amounts of energy with them, and a small fraction of those energy states are visible to our eyes. So the sun is the nearest significant radiator of light, and if you just look outside, you can tell that it's pretty bright. But a way to actually quantify the amount of light that it's emitting is its luminosity, which is the total energy radiated per unit time. And if we measure that in watts, which should be a familiar unit, we can actually just plug in an expression in Mathematica using these objects and properties of that object. So we can we can, or I guess this is called an entity. So Mathematica has an entity object in it called the sun, and we can ask for its luminosity, and it gives us 3.83 times 10 to the 26 watts. So that's an enormous value compared to something like a 60-watt light bulb. And even on Earth, which is 93 million miles away, we still have around 1,400 watts passing through every square meter of this electromagnetic radiation.
That's 1.4
So
kilowatts per square meter at this radius.
yes, I believe that's above the atmosphere. So the atmosphere blocks out some of that energy, thankfully, so that it makes us less likely to get a sunburn. But yeah, above the atmosphere, it's 1.4 kilowatts per square meter, perpendicular to the direction of sunlight. And so for a long time, this electromagnetic radiation or light was the only way that we could observe astrophysical sources, including the sun and other stars. Whether that was just looking by eye or with the aid of a telescope. But in the past 100 years, we've entered what astronomers are calling the era of multi-messenger astronomy, because we've also been able to detect other forms of radiation. In the 1960s, I think the first neutrino was detected. And this was a prediction that had been made for a while. And these particles are emitted in the nuclear reactions in the core of the sun. And so they also radiate away from the sun. And most of them actually just travel straight through the core. And the ones that do happen to reach Earth, most of those just pass straight through the Earth, because these particles they only interact through the weak nuclear force. And so we each have, I believe, trillions of these particles passing through us every second. And even though there are so many of them, they carry so little energy that they make up less than 3% of the luminosity of the sun. So just to give you an idea of how difficult these are to detect, this is a picture of the Super Kamiokande Observatory neutrino detector. And these neutrinos can only be detected through their interaction with matter. So what they do is they cover the walls, the floor, and the ceiling of this chamber, which is about 100 feet tall by 100 feet wide. They cover them with photomultiplier tubes, and they fill this whole thing with about 50,000 tons of water and just wait for a neutrino to interact with a water molecule, which happens only very rarely. But in the process of that interaction, there's light emitted, and these photomultiplier tubes can detect that light. But this is an amazing feat of engineering, because they have to bury it under like 3,000 feet of this mountain above it, so that they can eliminate other sources like cosmic rays and things like that. So that kind of summarizes all the types of radiation we can have, ignoring gravitational radiation, which will be the main focus of this talk.
That's interesting about neutrinos being 3% of the luminosity. So that's like if 1 square meter is like 1.6 kilowatts of solar, electromagnetic radiation, then like 3% of that's going to be tens of watts, essentially.
Yeah, yeah,
Is that luminosity even beyond our visual spectrum? That just like total light energy, or is that actually contributing to the brightness of the sun that we can see?
yeah. I believe the 1.4 kilowatts that I mentioned, I believe is the bolometric luminosity. So that includes all wavelengths of light, even the ones that are not visible to us. So yeah, infrared, ultraviolet, and all parts of the electromagnetic spectrum. Yeah, so there are other types of things that people would classify as radiation. Like I mentioned, cosmic rays are charged particles that have been accelerated by really strong magnetic fields. When the source of those charged particles is the sun, we call it the solar wind, and that those particles can interact with our own magnetic field and create the auroras. But those are fundamentally electromagnetic types of radiation as well, because they're carrying energy that comes from ultimately a magnetic field. So
I mean, these cosmic rays, again, they're very interesting, right? They can, like, one particle can have the force of like someone, like a solid punch, like
yeah,
a couple pounds of force.
yeah, yeah. So luckily, most of them are blocked by the upper atmosphere, and are the Earth's magnetic field also um, protects us as well. But yeah, they are very interesting sources, and there are a lot of cool experiments involving like balloons to detect these cosmic rays. Actually, I believe the first person to detect cosmic rays, I'm blanking on his name right now, but he won a Nobel Prize for it. And he would actually like risk his life going on solo hot air balloon missions to try and detect these things. But yeah, we've actually found in particle accelerators, scientists have found that the weak nuclear force is actually just another side of the electromagnetic force, and that at higher energies, those two forces are unified. So really, all of the types of radiation that we've described so far are fundamentally part of the same system. And the only force that we haven't really mentioned, other than gravity, is the strong nuclear force. And we don't see radiative phenomenon with that force because it's such a short range force. It can't really radiate energy in the same way unless it converts it somehow into electromagnetic, which does happen in nuclear reactions.
Right. So the electroweak is that holds the nucleus together.
The strong nuclear force is what holds the nucleus together, but the electromagnetic and the weak force, those are the forces that actually act on long enough distances to release energy in nuclear reactions. So even though it's the strong force which holds nuclei together, it's the electro weak forces which actually radiate energy away.
So I have a quick question about that. I was looking at this recently, and the claim is that all of the particle interactions can like fall under QFT. Is that the right word? Quantum field theory.
Yeah.
Because the weak and the strong force at high enough energies seem to be the same thing as like light, whatever the normal thing is. But then there was some caveat. They say with some exceptions, or there was some like footnote to that. I don't know if I was yeah, I don't know if you can elaborate maybe where there is still some discrepancy as to the total unification, or is that being dismissed? It's basically it's fully consistent at this point.
So yeah, I think as far as I understand it, particle accelerators have been able to actually probe the energy regimes where the electromagnetic and weak forces are actually unified and can be described under a single type of force or single type of interaction. But the other unification of the electroweak and the strong force, I think that there's kind of a sense that from the observations that have been made so far, it's plausible that that's the case, because of the trends that are observed as we go to higher energies. But I don't think that energy has been attained. So I don't think it's been verified, but I think it's consistent, perfectly consistent with
I
the.
see. So it's kind of like the theories are consistent, but there needs to be experimental, like fully conclusive experimental evidence still. Something
Yeah.
like that. Okay, cool.
Okay, so yeah, those three forces are all described by quantum field theories, but the kind of the one that stands out, the force that Einstein showed was really not a force, but more of a consequence of the geometry of space-time, is gravity. And so it turns out that gravitational systems can also radiate. And this was one of the biggest achievements in recent modern physics. So 10 years ago, in 2015, gravitational waves were first detected by LIGO, which is the Laser Interferometer Gravitational Wave Observatory. And this was 99 years after Einstein demonstrated their existence as a solution to his field equations of general relativity. So Einstein published his field equations in 1915, and then in 1916 he showed that we should expect these wave-like solutions as being a possible solution to his equations. And then 99 years after that, we were actually able to detect these waves. And this LIGO observatory is actually made up of two facilities. So this one here is the one in Hanford, Washington, and it's this ultra-high vacuum system, and it's an interferometer similar to one that that Albert Michelson used in his experiment to show that the speed of light is constant regardless of the observer. So there's an interesting kind of connection there. And again, even though we're measuring something that's a form of energy not related to light, we're still using light to measure this wave, because as observers, light is we kind of live in a world where light is the easiest thing that we can measure. And so the principle of this interferometer is that it measures it has a high power laser here. It splits the laser into two beams, and the beams bounce off mirrors, and then they eventually recombine. And if there's any difference in the path length between these two arms, then the beams of light will be out of phase slightly. So the crests of the waves will not line up, and so they'll interfere with each other.
So this is interesting because is it is it possible to just measure like one of those lengths, one of those legs by itself and just say, okay, I have a waveform and then it's bouncing back, and then you compare that waveform with itself, right? So if that mirror gets longer distance away, you can see in the interference a shifting, I guess.
Yeah.
And so you can tell if the mirror moved further or closer away based on the interference
Yeah.
of just one wave, hypothetically.
Yeah. Yeah. So there are other kinds of interferometers which can measure things like that, but yeah, ultimately it's only good for measuring really small displacements.
Right.
Because if you have a displacement that's larger than the wavelength of light that you're using, then you actually get the crests of the wave lining up again.
Mm-hmm.
And so they had to kind of choose these lengths carefully so that they can measure the right kind of displacements. And I believe that these laser lights are set up so delicately that they have another mirror here, and they bounce back and forth along these arms several times before they actually recombine. So any small change in distance there is going to be amplified because they'll travel the length of this arm several times.
Interesting.
And so, yeah, these arms are each 4 kilometers long, so a pretty impressive system here. And they need 2 of them to actually get good information. So this is the one in Hanford, Washington, and there's another one in Livingston, Louisiana. And they chose 2 locations that were far apart because gravitational waves travel at the speed of light. So they can synchronize their clocks accurately enough that they can actually find from what direction, or the general kind of direction the wave is traveling from. So yeah, the way that Einstein actually came up with these solutions is he considered small perturbations to regions of space-time which didn't have any mass in them. So he had already come up with the theory of special relativity, which describes those kinds of space which are called flat space, where there's no mass and therefore no curvature to the space. And so those kind of spaces have a Minkowski metric with a term, and the perturbation that he added to this metric is a term which we're going to call H, which is also referred to as the wave strain. And so he came up with this general form of the metric. If we didn't have these 1 plus H or 1 minus H coefficients in front of these terms here, then this would just be the Minkowski metric. but we can think of these coefficients as kind of stretching and squeezing in the x and y directions. And so if this h term becomes positive, we're going to have lengths in the x direction are going to be stretched by some amount, and lengths in the y direction are going to be contracted. And so when we're considering what kinds of systems can actually produce a metric like this, it turns out that a spherically symmetric distribution of matter can never emit gravitational waves. And this is a result called Birkhoff's theorem. And this basically results from something that Newton was aware of, which is that a spherically symmetric distribution of mass to an outside observer is consistent gravitationally to all the mass just being concentrated at the center of that sphere. And so if you have some spherically symmetric distribution, even if it's expanding and contracting, like you have with the collapse of a star leading to a supernova, because that's roughly spherically symmetric, to an outside observer, it's gravitationally speaking, in terms of the curvature, it's roughly equivalent to just all the mass being concentrated at the center.
Wait, so in the far field, like gravitational limit,
Yeah.
it doesn't matter if you have a mass that's spread out, spherically symmetric, or concentrated into a black hole, let's say.
Yes. Yes.
That like outside the event horizon, at least.
Yeah, exactly. So, so if Earth suddenly collapsed into a black hole, then the International Space Station would just keep orbiting around it in the same manner, because yeah, that having all the mass concentrated at the center in the far field limit, at least it doesn't make a difference.
Okay.
But when you do introduce asymmetries, such as when you have a binary system, then you get effects that are not consistent. And in particular, you can think about the Earth-Moon system. You get these tidal effects, where the moon creates tides on Earth, and the Earth tidally distorts the moon as well. And so these binary systems, we can think about these tides as actually traveling out into the curvature of the space-time continuum. And that's essentially what gravitational waves are, is this tidal energy being dissipated outward. So for something like the Earth-Moon system, even though we're dissipating gravitational waves because of this binary system, in practice, we can only detect these waves if they involve massive compact objects. So we're talking about objects that are much more massive or comparable to the mass of the sun, and very compact, meaning they can be close to each other without colliding. So neutron stars and black holes are the perfect examples of those. And so these are the only kind of systems we've been able to detect with gravitational waves so far, are these binary neutron stars and black holes. And so there's a lot of math involved with solving Einstein's field equations for a binary system like this. But kind of skipping over all the math, we arrive at a formula for this wave strain term, which depends on
this wave strain. It's like in one direction it's squishing, and the other direction is like pushing out.
Yeah, exactly. So so I
Like,
have a
can you get a strain that's just unidirectional, like just compressing the x direction, let's say?
I
Or does it have to like
I don't think so. I think if there's
does
if
it have
it's a
to go
region,
somewhere that pushing and you like get the
yeah,
same volumes?
I think in order for it to be consistent with the field equations for empty space, where it's a region of space without any mass in it, then there has to be this kind of reciprocal relationship where stretching in one direction corresponds to squeezing in the other direction. Because I think otherwise, if you only had one direction, that would be a solution that implies there's some kind of mass distribution within your space. So I guess on the surface of Earth, this is probably just an approximation because the Earth's gravitational field is going to affect this metric as well. But one of Einstein's thought experiments was that if you're in a small enough region of space, the gravitational field of the Earth, for instance, is going to be roughly uniform. And so we can still kind of use this, even though it's only going to be approximate. So yeah, the general form of this wave strain, and I guess another thing that I'm going to talk about a little bit more on the next slide is that this wave strain and these waves in general can have different polarizations. So this is just one form that's polarized along the x and y directions, but it turns out we can actually get polarizations that are rotated 45 degrees relative to that. And in that case, you actually do get kind of a more uniform stretching, at least if you're measuring still in the x and y directions, and the wave is polarized at 45 degrees, then you actually won't be able to measure any effect if you're just using the path difference between the x and y, because they get stretched uniformly in the case of that polarization.
Right. So, going back to the leg of
Yeah,
having two legs to it, two
yeah.
beams. So if it was just one beam, would they be able to detect space stretching and squishing along that direction? Or because it's weird to think about because the light propagates over space. So if you have something that's like 10 wavelengths long and you stretch the space out, it stretches the wavelengths out. And so like the light can't detect things under it. Maybe or I'm wrong about that.
I think it would be possible with one leg, but to measure changes in that direction. But the problem is if you only have one, then you don't have any information about the polarization of
Right.
the wave. You just know that there's some kind of wave strain passing through, but it doesn't tell you how it's oriented at all.
Right.
Um,
You just know that it could just stretch perpendicular to your line, or it could be you're picking up a horizontal component on a different compression. And so, having two enables some metric on directionality of the
yeah, exactly.
gravitational wave. And then having a different somewhere else on Earth, you have you can pick up based on if you have like on the surface of the Earth, you have like two lines here and then two
Yeah.
lines here. They'll be, you can get three-dimensional polarization information that way.
Yeah, exactly. So that was one of the main motivating factors with having two observatories, is that in this setup where you only have one observatory, you're only able to measure polarizations. I mean, you can measure other polarizations, but if there happens to be a system that's orbiting 45 degrees relative to your setup, then it's going to compress and squeeze space in the same manner for both the X and Y directions. And so that's the benefit of having two observatories, is that you can orient them 45 degrees relative to each other and pick up any possible polarization.
Now, is this, are these are orthogonal though, right?
So I just wanted to quickly check on how we're doing on the actual presentation itself. I need to leave in 5 minutes as well, so I just wanted to check how we're making progress with time.
Okay, yeah, I can speed it up a little bit through the background stuff.
Yeah, I just want to make sure we get into the actual content.
Yeah, definitely.
Yeah.
So yeah.
Just to
Kinda
be clear,
go
I have
through-
time to continue the presentation.
Yeah, you can go as long as you want. I just wanted to check that we get to the meaty stuff.
Yeah, definitely. So just to finish up this page, after solving the field equations, we arrive at this form for the metric. So it's a traveling wave which decreases with the distance from the source, which we're calling the z direction here. And the closer the r here is the separation between the two masses. So the closer they are to each other, the smaller this is, and the larger the amplitude is. So I have a little animation that kind of helps illustrate that. So this is the form of the wave strain, how it looks. And on the x-axis here, we're plotting the distance from the source, just ignoring the constants, so that we can get a good picture of it. And then on the vertical axis, this is the wave strain. So we can see closest to the source, there's the largest wave strain, and it drops off. And these waves will travel out at the speed of light. Okay. And it turns out that the period of the gravitational wave is half of the orbital period. This happens because if we imagine two equal masses, after half of the orbital period, they basically swap places. But if the masses are identical, then we should expect the same kind of wave strain is produced in that situation. So these waves oscillate twice as quickly as the masses orbit each other. And in the orbital plane, because from our point of view, if we're looking at the system edge on, we just see the masses going back and forth. That corresponds to a linear polarization in that direction and the direction perpendicular to it. But if we're looking along the axis of the orbit, we get a circular polarization, which is a little bit harder to visualize, but we can think about that as a superposition of linear polarizations. And this is kind of a visualization I made of the wave strain. So you can see that it alternately stretches and squeezes the space in the horizontal and vertical directions. Okay,
Right, so yeah, that's squeezing the x direction will like push out the y direction to compensate.
Exactly, yeah. So this is like a two-dimensional slice of a space that a gravitational wave is passing through. And we could think about setting up our interferometer along these axes. But if we set it up at 45 degrees, we wouldn't be able to detect it.
Right.
And then using the field equations as well, you can consider the effective contribution of these waves to the stress energy tensor. And that gives you an expression for the luminosity. So instead of amount of light energy emitted, this is the amount of gravitational potential energy that's emitted by the system per unit time. And ignoring the constants for now, it's proportional to the sum of the masses, the product of the masses squared, and it's inversely proportional to the fifth power of the separation. So these waves they emit the most energy when the masses are close to each other. And for example, if we halve the distance of the masses, then we increase the luminosity by a factor of 2 to the power of 5, which would be 32. So it's very strongly dependent on the separation. Okay, and then because this is the change in energy with respect to time, we can relate that with the change in radius with respect to time, because we know, or the change in orbital separation with respect to time, because we know how much gravitational energy there is at a certain separation of the objects. And so then we can just integrate to find the radius as a function of time, and we can use that to find how much time needs to elapse for the separation to go to 0. And this is called the in-spiral time. And so that's actually, compared to the previous calculations, that's actually not too difficult to do from just this information here. And we also know the frequency of the orbit as a function of the separation. So we know that as they get closer and closer to each other, they're going to orbit more rapidly. And we can calculate the frequency evolution as a function of time. And it depends on a parameter called the chirp mass. If both the masses are equal, this number just turns out to be approximately equal to just either one of the masses. So we can think of it as like some kind of average of the two. So if this chirp mass is large, the frequency of the spiral is going to go down. And if it's smaller, the frequency is going to increase. And it actually turns out for a certain range of chirp masses, this frequency is actually in the audible range, which I thought was pretty cool when I first learned that, because you can just use this function to actually generate audio of what it would sound like for two massive objects to collapse. And so I did an audio clip of just
awesome.
using that formula on the previous page. I made an audio clip of two neutron stars collapsing, spiraling in towards each other. They're each 3 solar masses, and they start at a separation of 300 kilometers. So hopefully you can hear the audio. Did you hear that?
Unfortunately, not. You're not sharing
Oh,
audio on your Zoom.
is there a way I can share audio?
Yeah, how do you do that? Dugan, I really want to hear what this sounds like.
Oh, okay. I found the option where I can share sound. So so let me do that now.
Hopefully you don't get an echo live stream. Yeah, go ahead.
You heard it?
Yeah.
Wow.
Okay.
Okay. Oh, that was amazing. I'll
Yeah.
watch the rest of the recording. Thanks, guys. That was great.
What was that?
He has to drop off.
I'll watch the rest of the recording. I need to drop off. That was awesome.
All right.
Awesome. Okay, so yeah, that was 3 solar mass neutron stars colliding, and yeah, I thought that was really cool that I was able to generate that audio just from the equations that we found there. And for 2 larger objects, because the frequency spectrum is shifted down, it's kind of hard to hear. Maybe like if you released 2 magnets and but yeah, for smaller masses, it makes a very clear pitch. For these larger ones, it kind of sounds just like 2 things bouncing off each other. Okay, yeah, so you can also look up audio clips of LIGO data that's actually been turned into sound, and it sounds pretty similar to this, which I thought was pretty cool. Okay, so now we're kind of getting into the actual purpose of the project, which was we wanted to create a discrete model for gravitational waves. And we're going to start with motivating why we would actually want to do something like that, where the continuous space-time model has been pretty successful at making a lot of predictions. But the issue is that general relativity in general is not theoretically consistent with quantum mechanics. And the reason for that is related to the fact that quantum mechanics, it requires that energy in all forms is quantized. But in the mathematics of general relativity, we're allowed to have any amount of gravitational energy. And quantum mechanics kind of forbids that because it says that you can't have an arbitrarily small amount of energy, and that energy has to come in discrete quantities. So
Right. So like if a photon of the smallest quantized energy possible is emitted from a distant star, let's say, and then there's all this red shifting due to the space time in between being stretched by like the Hubble constant, let's say, right? So there's redshift. The further out you go, the more redshift you get. So if you have a redshifted photon starts out at the smallest energy and then it's redshifted to a lower energy, is that still a photon? Or is that still detectable? Or I guess that's an inconsistency that arises.
Yeah, exactly. There are a lot of kind of thought experiments like that kind of lead to inconsistencies with the 2 models. And ultimately what theorists have tried to do is they tried to find a particle representing a single quantum or a single unit of gravitational energy, similar to how photons were found to be single units of electromagnetic energy. But the problem is if that particle were to exist, and it's a hypothetical particle, which is called a graviton, and if we wanted to include this in the standard model of particle physics, it would have to be a spin 2 gauge boson. And the fact that it's spin 2 actually relates to what we discussed with the the polarization states. So we said that fundamentally, if it's linearly polarized, it can have this plus polarization, or what's called a cross polarization, where it's at 45 degrees. So if we compare that to the polarization states of a photon, the independent polarization states are just either vertical or horizontal.
Yeah.
So a photon is a spin 1 particle, because if we think about rotating the polarization state through 180 degrees, we go through all of the possible states just a single time. Because when we get to vertical, we get to this independent state, and then when we go a full 180, we're back at the original one. But if we think about a gravitational wave, if we were to try to quantize it, it has this property of being of having like twice as many polarization states per rotation. And so that's why it would be a spin 2 particle, whereas the photon is a spin 1 particle.
That made some sense to me. I think I rocked something.
Okay, good. Yeah. The basic idea is that like a gravitational system that you're looking at edge on, if you detect a gravitational wave in this plus polarization, for instance, you won't be able to tell if that system is actually orbiting up or down from your perspective, or left and right.
I see.
But for the case of polarization of photons, you can make that distinction. So that ambiguity in the polarization of gravitational waves means that if you tried to quantize it, it would have this property of which theorists called spin 2. So the problem with that is that theorists have studied hypothetical spin 2 particles, and they found that the fields representing those particles are not renormalizable. And this is this procedure of renormalization is a standard procedure that has been done in quantum field theory in order to make calculations consistent across all scales. So in order for you to be able to take the limit, for instance, if we think about the electromagnetic force, the force of the electric field between two particles is proportional to the inverse power of distance. But if you want to create a theory that's consistent as you take the limit, as the distance goes to 0, you arrive at infinities that are kind of hard to do away with unless you use this procedure of renormalization. And the problem with making a graviton that fits with the standard model is that you can't renormalize it. So that's one of the main motivations for going discrete. And that's why people have come up with theories like quantum gravity to try and describe this. And the idea is that the problem, the reason why there's this inconsistency is that we're assuming space and time are continuous, but we wouldn't have this problem if space and time were made up of discrete points, because if that were the case, we wouldn't need to take limits as distances go to 0, because there wouldn't be an infinite number of points between any two points in space and time. There would be some fundamental unit of space or unit of time, which is necessarily much smaller than anything we've been able to measure, because we haven't seen the effects that we would expect for a discrete space-time geometry. And there are a lot of challenges with trying to do this. So one of the ones that I encountered, or the one that I was trying to wrap my head around the most, was trying to preserve the notion of direction without compromising the fundamental isotropy of flat space. So the isotropy just refers to the fact that if we start with a two-dimensional space as an example, for instance, this computer screen, it's not clear that there's any preferred direction, and our laws of physics shouldn't have some preferred direction to them, because we observe the same kind of processes happening no matter what direction we're looking in. But if you try to discretize this space with like a grid of points, then what you're doing is you're fundamentally ruining the isotropy, because now there's a preferred direction. However you choose to lay out your grid necessarily invokes these preferential directions. So there's kind of a give and take between trying to preserve those notions of direction without picking out any one of them preferentially. So that's something that I tried to grapple with these models. And then the other one is that if space-time is represented by a network of points and a causal network showing the relationship between past and future points in the network, it's not clear what additional structure we might need to preserve the notions of geometry. So if we go back to the example of the grid of points, if I preserved the connections between all of those points, but jumbled them all around in the space, so that all of the only information you had was just how they were connected, it's not clear that you would be able to reconstruct what the space looked like just from how it's connected. So it's possible that the network might need some additional structure to preserve geometric notions. So yeah, those are the two main challenges, but we'll. Yeah. Yeah. So I did, in some of the initial conditions I used like a randomization process to select how the initial nodes of the network were distributed and connected. So I think that does probably have to be, that has to be something that's necessary for doing these kind of experiments. And then in a more like general sense, if we want to understand these models beyond doing just these computational experiments, it's likely necessary to do some kind of statistical analysis of the physical processes involved. So I'll go over kind of the Wolfram class of models quickly so that we have an understanding of what kind of models we're trying to make. And the general idea is that we're we're discretizing space-time, and we're looking at space-like hypersurfaces. So these are surfaces that basically pass through an event, and they don't they're basically perpendicular to the light cones. So no two nodes within that hypersurface can directly affect each other. They can only affect each other through interactions in the future. So that's why it's called space-like. And these graphs are generalizations of networks. The class of models is general enough that it also includes hypergraphs, which can have connections involving more than two nodes. But in this project, I just focused on graphs. So each edge in my models can only connect two nodes. And so the temporal evolution of the system is determined by a set of patterns and rules of replacement for those patterns. And you can choose to replace in any order. But certain replacement rules have this useful property of being causally invariant, meaning if we chose a different order of replacement of some pattern in this network, we can always get back to the same network from each of those branches that split off. You can always get back to the same network in a finite number of evolutions. So that's something I was trying to keep in mind when I was looking at rules, was these causally invariant rules are the ones that have the most potential to represent a space-time model. So it's sufficiently general to allow for the ideas that are encapsulated in relativity, in the sense that different observers could apply replacement rules in different orders depending on their state of motion within this network. And therefore they can measure different notions of time and space depending on the way that they apply these rules. But if there is causal invariance, it's relative in a self-consistent sense. And so in each reference frame, we expect that the evolution of the graph is, and the points in the space are independent and absolute. And so for similar kind of ideas, I was looking into formalism that's equivalent to Einstein's field equations, which uses the same idea of space-like hypersurfaces, and that's called the ADM formalism. So if you're interested in that, you can look into that, and it's used in theories of quantum gravity and also in numerical simulations of general relativity. And so those kind of ideas are what were the guiding principles of this project.
Yeah, makes sense.
Okay, so I started really simple because it wasn't really clear where to start. So I was just looking at first on graphs involving 4 vertices, because I was thinking in terms of how one might observe a wave within this network, and the Michelson interferometer that LIGO uses seemed like the kind of perfect setup that I could try to measure these waves within this network. And so I started with just 4 points. And it turns out that if we're looking at simply connected graphs, undirected graphs where the orientation of the edge isn't specified, there are only 6 of them up to isomorphism on 4 vertices. So I started with these 6 graphs and was kind of just thinking about which ones would be the most promising. So I chose these bottom 2 in the bottom left here. So this is the cycle graph on 4 vertices, and this one's called the diamond graph. And for the moment, I was just kind of interested in this 2-dimensional slice of the system, and I created a replacement rule where we could oscillate back and forth between these 2 states. And I was actually able to, in general, these replacement rules are defined on directed edges. So I was able to find a rule which worked on the directed versions of these graphs, which actually oscillates back and forth in a similar way to a gravitational wave. So I used these 2 replacement rules where the X, Y, Z, and W here just stand for 4 arbitrary vertices. And so the first replacement rule basically looks for a connection of 4 vertices in a cycle, and then it replaces that with kind of the same cycle here. So these are the same 4 sets of edges, plus an additional edge between X and W. And then this replacement rule does something similar, but kind of in reverse. And it also changes the orientation of some of the edges in a way that we can get this alternating pattern. So if we start this on a certain directed graph, after 1 evolution, we get a edge connecting the upper and the lower vertices, or the nodes in this graph. And then that edge disappears and it reappears, but now in the horizontal direction. And so this is kind of exactly what I was looking for, because if we use the graph distance, or the number of edges that you have to travel to get between 2 nodes, as a measure of the distance, we could imagine sending using a beam of light traveling through this network to try and measure the distances here, and we would find the same kind of changes in distances that we expect for a gravitational wave. So yeah, we can imagine that the 4 points form kind of our own Michelson interferometer gravitational wave observatory, and we can use that to measure the wave strain by finding the difference in graph distances. So when we do that, we get something that looks like a discrete analog of a wave. But this model was kind of just to get me thinking about more general ones, because again, we just have a 2-dimensional slice of space, but I wanted to see how it worked on larger lattices. And so if we preserve that kind of cycle shape, but we add more points in this grid pattern here, depending on the different initial conditions that you use, you can get different kind of behavior. So some of the waves, in this simplest case, it's the same, where the wave strain just goes up and down with a period of 4 evolutions. But with these different initial conditions, it still has that overall pattern, but there's a little bit more complexity involved. Because there's a little bit more asymmetry in the initial condition. Okay, so I wanted to generalize this to 3 dimensions. So I considered a rule which would kind of take this diamond graph and transport it through a 3-dimensional lattice. And so this would be kind of analogous to how a gravitational wave perturbation spreads out and travels at the speed of light. And so I wanted to find a rule which could evolve this perturbation through the lattice. So I found this rule, which is a little bit more complex now because we're dealing with 3-dimensional graphs. And so here I have X, Y, Z, U, V, and W. So now we're dealing with a pattern of 6 vertices within this graph. And we're changing that pattern so that after every evolution, this horizontal edge here is transported to the right. And so I wanted
are these graphs oriented? Are you using the orientation, the like sort of rightward orientation?
Yeah, exactly.
Somehow.
So in this particular setup, I haven't shown it in the pictures here, but the edges are oriented. These edges between the nodes here are oriented towards the right, which is how the edge travels to the right and not back to the left. So this is it does depend on the direction of the edges. And so I wanted to generalize to a directed graph where instead of having a certain orientation picked out, I just put directed edges in both directions. And I wanted to see what would happen if we just kept evolving that system. And so if you replace all these edges with directed edges going both ways, you end up at the same final graph, no matter how you evolve the system, even though there are multiple ways to go about it. And so you always arrive at this final graph, and this graph doesn't have any of the patterns given by this rule replacement here. So you can't evolve the system any further after this. And like I said, the particular choice of the order of replacement rules does affect the particular evolution that you get. But because you always end up at the same final graph, no matter what order you choose, that shows that, at least for this choice of initial condition, the replacement rule is causally invariant. And we can actually show the causal relationship between the different evolutions. So at the top here, this is the initial condition, and the bottom is the terminal graph that we always end up at. And even though you have different choices of the initial evolution and which nodes you replace, you always end up back at the terminal graph there. So this rule was pretty promising in that regard, and it had the kind of structure I was looking for. And so the next thing I did was I set up some initial conditions using this rule, and I wanted to use the same method of the graph distance to measure the wave strain. Okay, so yeah, there's a function in the Wolfram function repository called discrete hypersurface decomposition, and it creates an initial network based on a given metric. So I used the metric that we saw for linearly polarized gravitational wave, and I wanted to see if I could recreate the evolution of the wave strain that we had in the two-dimensional model. And I wasn't very excited with this. First of all, I wasn't quite sure how the discrete hypersurface decomposition was working. And I did read up on the source code for that. And
that was written by Jonathan Gorard, if I'm not mistaken.
Yeah, so again, it is related to the ADM formalism, where we're using a metric and finding an initial hypersurface. And if we were doing a numerical simulation using general relativity, there's a way to do that with the ADM formalism. But here I just wanted to use that as an initial condition for this Wolfram model. And it does use a randomization procedure for distributing the initial points, which is why I was interested in using it, because like we were saying earlier, if you just choose a lattice, it doesn't have this property of isotropy that we're looking for. But this randomization procedure that's used for numerical relativity has been shown to be pretty reliable. And here, when I evolved the system, I did kind of get some oscillatory behavior, but the wave strain wasn't oscillating around 0. And I wasn't sure if this was just because of the order of the replacement that I was doing. But in the future, I do want to kind of revisit this and look at the causal structure of the evolutions and how you can choose different orders, and maybe make a similar kind of graph, but average over all the possible states that you could be in after a certain number of evolutions, because maybe in that aggregate, I might get more reliable results. But the main kind of limit with this whole project for me was the computational time was just very expensive, especially because this rule is a little bit more involved than a lot of the Wolfram models. It's searching for a pattern of 6 vertices connected in a certain way. And so it's just very computationally expensive to evolve this system. And that's why I wasn't really able to consider, in these cases, different orderings of the replacements. But I think I might want to do something like that in the future. And then I wanted to, even though this clearly wasn't a randomized distribution, I wanted to try a nearest neighbor graph, where I used that perturbed metric for a linearly polarized wave as a notion of distance. So these points are evenly spaced, but in terms of the edges that connect them, they use the metric for the gravitational wave to determine the nearest neighbors. And here, because I was interested in how the wave strain evolved not only in time, but also over the spatial extent of this graph. I basically set up using that same interferometer concept. I set up one interferometer at every single z direction, and this was the direction that I expected the wave to propagate along. So if we look at the animation of how the wave evolves, I think if I kind of squint at it, I can convince myself that it's moving to the right. But again, there wasn't really like a promising result here. And we do get this kind of freeze out where I guess the strain just builds up. And because of the boundary conditions that I have on the graph, there isn't really anywhere for the gravitational energy to go. And so I suspect that it kind of just piles up on one side of the graph. And so that's another thing that I want to try is maybe using different boundary conditions to see if there's a way to show the wave just passing through the boundary and maybe dissipating somehow, just imposing different conditions on the boundary than what I have at the moment. And then I wanted to do a similar kind of thing, but here instead of using evenly spaced points, I spaced them closer together according to the metric, or farther apart if they were in a region that was stretched out. So we can kind of see if we rotate this a little bit, that it has a structure where it's stretched in one direction and squeezed in the other. And I wanted to see, since this is kind of similar to the visualization I did for the linearly polarized wave, I wanted to see if this would evolve in a similar way. And I did not really have much luck with that either. And here the wave strain along the z direction, again, it didn't really travel in any sense. And in terms of the temporal evolution, it kind of just relaxed in some sense before freezing out again. So just for fun, I also wanted to see what would happen if I started with a kind of wormhole-like structure. So I started with these two strongly connected clusters that were connected only by this narrow bridge, just a pair of edges going back and forth. And so after 20 evolutions, I was kind of pleased with the results that the clusters just combined with each other. And so I was pleased with this because wormholes are something that have been studied in general relativity, and it's pretty much been found that if you were to construct something that resembles a wormhole, you wouldn't be able to travel through it because it would just collapse so quickly that that there wouldn't be enough time to travel through it. And so I was kind of happy with this result because it shows that same kind of behavior of the wormhole collapsing in a sense. And we can see that in the evolution of the clustering coefficient as well. So yeah, that was those were pretty much all the initial conditions that I tried. Like I said, each one of these experiments took a lot of computational time. So I think I might need to try a little bit more of a analytical approach before trying to do computations like this, just because it is so expensive computationally, and when you get a result that's not very fruitful, then you kind of just realize that, oh, like maybe I need to think about the logic of this a little bit more, and do a little bit more work by hand. So yeah, that's kind of where I plan to go in the future. So even though I didn't really have much success resembling gravitational waves with the Wolfram model, I did explore a lot of interesting ideas, and I learned a lot about general relativity in the process, which was great. Yeah, I think the most difficult challenge that I have with this is trying to find a correspondence between the pre-geometric notions of just how the graph is connected with edges, and find the correspondence between that and the more familiar properties of space-time. Like I said before, I think there's a lot of statistical analysis to do, and statistical mechanics has been a big part of modern physics as well. And yeah, I think instead of just measuring the graph distance, I also think it would be great to try and model photons or light actually traveling through the network, because that's actually how an observer would measure a gravitational wave. And so that seems more realistic.
Oh, Nate, just one question, or
Yeah.
kind of two. I think the idea of using like the metrics to influence or define the like just the graph connections is interesting. But do you think, like, I think that's actually a good idea, but then maybe you could use those defined just regular graph connections to influence, like, I mean, you could try hypergraph sort of thing where, if four nodes are connected, or if they're kind of form a cluster of regular graph edges, then maybe you define some hyper edge, and then it's hard for me to imagine what that would change or how that would change things, but I think you could like have the metric define the regular graph connections, or maybe you could even start with higher arity connections. But I wonder if that would give you more kind of room to like encapsulate what's going on. I think like maybe it would be more difficult with just the regular graph edges to like, again, computationally, maybe that would make it harder. But maybe there's some like analytical work to be done. And then I guess just I don't know if you tried that, but then the other thing I was just wondering is about like, what is the causal invariance? Like, do you have a physical interpretation of what that kind of gives you? If you have, say, causal invariance, like, what is that important for?
Yeah. Um, so for the first part of the question, I did kind of look into higher arity relationships, but I wanted to start with just simple graphs before going on to hypergraphs, because I wasn't really as comfortable with those notions. But I do think that would add some more interesting structure, and maybe that's the structure that's actually needed to define the geometry of the network.
Mhm.
And then for the causal invariance part of it, my understanding, I read some of Jonathan Girard's work on the correspondence between these models and general relativity, and it seemed like causal invariance was a necessary condition for these models to actually be used
Mm.
in in a way that would simulate relativity. And my understanding of that um, is that if a rule is not causally invariant, then um, then these branches of possibilities can kind of split off and never recombine with each other. And so in that sense, it doesn't give you a self-consistent description of the laws of physics, because you could choose to replace in one order, and that might lead you down a branch that never that could never be reconciled with some other branch.
Okay, interesting.
Yeah. So with a causally invariant rule, even though you have this branching phenomenon, um, it's kind of similar to how in a quantum system, you consider all the possible paths of an object throughout space. And it gives you a result that's self-consistent. So even though there's all this branching of possibilities, it doesn't matter which branch you actually took to get to the final result, because they all will eventually recombine.
Right. Okay. Okay, that makes sense. That I can see that.
And so, one question I have is, you use the same rewriting rule to have all these updates?
Yeah, so from my initial kind of toy models with thinking about kind of these simple graphs on 4 vertices, and then kind of larger lattices, I use the same rule on all those initial conditions. But obviously there might be a rule out there that's a little bit better. And I did do some experiments with other rules, but in my final project report, I just wanted to focus on the one that was most promising.
Yeah, it'd be interesting for future work, or for other people to pick up this type of project, to look at rewriting rules that are like more aware, more topologically aware. So like large rules that look at a larger patch and see, okay, well, oh, maybe it's stretched in this direction. So like the updating rules to kind of bend it more, or bend it to react to topology. And if it's possible to say, okay, we know what the metric is insofar as we know what the edge distances are, then there might be a way to look at updating rules that respond to the metric itself. But yeah, so there's a lot of room to explore like different updating rules and different initial conditions.
Yeah, that's something that I thought about as well. During when I was at the summer school, there was a presentation by Oliver Nill, and he had a lot of good ideas about how you can generalize notions of calculus to graphs. And so that kind of got me thinking about the same idea of like using the form of Einstein's field equations, how they relate the metric to the mass and energy within a certain region of space. Using that to maybe find a rule that corresponds to the metric a little bit more closely.
Well, and as Dugan said, like I mean, depends what you mean by this, but like more topologically aware sort of rules could mean that, like, I mean, again, you could start with just the metric defining these regular graph edges, but then like if you have a certain cluster, maybe like in the lattice models, I felt that was pretty easy to imagine because you have these like squares essentially, and like you could just think of four hyper edges kind of creating a, you know, a in the visualization, it would just be like a surface connecting those four edges, and you can, and maybe then that gives you like, you can then start to, the hierarchy connections would give you more kind of global like encapsulation rather than just like, you know, you have these very localized regular graph connections. I think that, and like it's easy enough to kind of slowly build up, especially with some of the models that you had worked with, just because they're rather still structured. And I wonder if rewrite rules there could be expanded on.
Yeah, definitely. Yeah, so I guess I also just wanted to acknowledge my mentors at the summer school. So John Marco Morbelli and John Lederman were really helpful in kind of working through the issues with the project. All the members and administrators at the Wolfram Institute and the summer school is a really great experience. My teachers at UCLA and of course my family. So
Very
yeah,
cool.
I think I'll stop sharing my screen.
Thanks, Nate. That was great.
Yeah, no problem.
Yeah, thank you very much for coming on and presenting. Very interesting work.
Yeah, no problem.
All right. Thanks for everyone who's tuning in, and see you again next time. Just some announcements. Wolfram side, there's a community forum on our Discord on, I believe, Wednesday the 2nd. So tune in for that. We'll have good discussions. The theme is going to be on geometry in general, so that should be fun. Nate, thanks once again for presenting.
Yeah, no problem. It was
Last
a
live stream, and bye for now.